Recording. All right, now we're getting to chapter 8. Hopefully we're getting a little bit ahead of the homework here, so you're prepared for them. All right, what we see here are some data points that are somewhat curve-like, in how they're distributed. As a human, you can see that very easily. And you can, in your mind's eye, estimate where that line should go. But computers aren't like your head. So you have to give them something to work with. And just like we've been talking about, you can choose a linear model. Just y equals mx plus b. And that would do reasonably well, right? You're just minimizing these errors, right? You're minimizing the square of all of these. Then we see another model, which is a degree 3. So that could mean it's got maybe up to x cubed in it. And we got a degree 5, which could mean up to x to the 5th, And you got these different models that can get closer and closer to fitting those points perfectly. And if you remember, if you go high enough, you can always find something that will fit them perfectly. But that's not good, because you don't actually want to fit it perfectly. You'll be overfitting. So what this slide is about is just one thing. This right here. How do you decide which model to keep, which is not overfitting? There's not just one way. There's many different ways. And this part of the Zybooks is just teaching you this one way. Let's say we try a whole bunch of models, and one of them has really low error. Maybe it's this one right here. It's the lowest error. And this could be, a degree 6 model. Then what you do is you look one standard deviation away from that and see which other models are within a standard deviation in terms of the error. So what you're seeing here, this is just the error, mean squared error. Remember that RMSE thing we keep talking about? Root mean squared error. It's just the root of the mean squared error. Basically, you can just think about one or the other. But you have mean squared error here. This is your degree 6 number. So, and a y equals mx plus b up to x to the 6. That's a really complicated model. Maybe n1 plus m2 x squared plus m3 x cubed, all the way up to x to the 6, and there's a plus b at the end. I mean, this is way overthinking it. You're basically never going to want to actually use a model like that. You want to use the simplest one possible. Now, what they suggest here is, let's say you have the 6th one, and this is the error, and then you have this band around it, one deviation above and below, and you find all the other ones that are within that. It looks like the 3rd is within that. I don't ever do this. What I usually do is I look for something good enough that explains a lot of the variance and doesn't have too much error. Look at this drop right here. Degree 1, the straight line. Degree 2, with x to the squared. And then it drops up real quick at this 3. And then you don't get any benefit of 4th or 5th. So this is a good spot to stop. As soon as you have enough parameters to get that error drop, that's probably a good place to stop. And in 2 dimensions, obviously, you can see with your eyes and get a sense. But in higher dimensions, you won't be able to do that. So you have to look at things like the error dropping. These are other examples that are very obvious when you look at it. Underfit. Linear model is not good enough because we can see there's kind of an arc to the data. And this arc, that fits it pretty good. Intuitively, it gives you a good sense. There's still a lot of error. This is very little error. But the fact that there's multiple bumps in there, if you don't have a theory to tell you why those bumps should be there, then this is a bad model. You need to understand the underlying mechanism. Why is this data coming out this way? It's going to be different for every kind of data set. You just make simplicity better. Simplicity better. Other examples. Who likes A the best? The top left. Raise your hand. And you have to raise your hand for one of these. Okay, we only have one person for A, 2 people for A. Who likes B the best? All right, about 4 or 5 people. Who likes C the best? Who likes D the best? Most people. All right. I'm conflicted between A and D, but I probably like A the best. Now, this is losses incurred by insurance agencies. Typically, an insurance company is going to have an equation behind the scenes that involves many factors, not just one. If it's car insurance, it could be, your age, it could be the kind of car you drive. There are some states in which if you have a sports car, if it's red, you pay more insurance. Because they found that people with red sports cars drive less safely than people with other colors. So you want to have an understanding of the factors and how they can affect your output variable. If you're going to have weird peaks and bumps, you want those to be explainable. I don't know if any of you have gone shooting, but think about a target. Let's say you have a nice tight cluster, but it's always in the same direction, like top left. It means you have a low variance, but you've got a bias. You're shooting up to the top left. Maybe your bias is low and to the right. But if you have low variance, you've at least solved part of your problem. You just need to get your bias on. Models can do this too. High variance and high bias is the worst. Low bias, low variance is the best. And this, of course, is high variance, low bias. So whenever you're trying to remember what bias and variance are, this is a good visual to keep in mind. So what we're talking about here are different ways that models have errors and how to judge them. Bias and variance, you often think about them at the same time, and you're trying to minimize both and find that perfect one in the middle that's going to have, the low variance and the low bias on test sets, not just what you train it on. This is a simple confusion matrix. Let's think about a binary model that's just telling you true or false. Let's say maybe it's a cancer diagnosis model. It's going to look at your scans and tell you you have cancer or not. The best models will have everything here or here, and none of it here or here. So this is a type 1 error. If you say they have cancer, but they don't actually. False positive. Here's the opposite. If you say they don't have cancer, but they actually do. And for cancer, this is the most dangerous place. Because if you actually do have cancer, but the test tells you not, then you won't change your diet or whatever else. You won't do medications or treatments, and you could end up dying of something that you could have prevented. So for cancer, this is the most dangerous square. Another case is if you have a list of terrorists that you're looking for at the border, or boarding planes or whatever. If you say they're not a terrorist, but they actually are, that's very dangerous there. But there are cases where you don't really care as much about false negatives. And maybe you want to focus more on these kinds of errors. What are some binary tests or models that you might have heard of instead of, the cancer diagnosis stuff? What are some others that you might have thought of? Binary models, it's true or false. Do any of you watch the show Silicon Valley? It's a stupid, silly show, but it's funny. And this guy made a visual model. And he said, look at this, I can point my camera at a hot dog and it'll tell me that it's a hot dog. And he points at the hot dog and says, hot dog. And everybody's like, psyched because it works. This was a few years ago when this was still new. And then the boss is like, all right, awesome. Now point at the pizza. Points at the pizza. Does anyone know this? This is not hot dog. And the boss was so disappointed, like he expected it to say pizza, but the tech guy who built it, he was like, yes, successful. This hot dog versus not hot dog. That's a very low stakes situation. If you get it wrong, who cares, right? What's another binary model you guys might have heard of or thought of? Or could think of right now?
Like looking at the screen, medical test data, positive.
Mm-hmm. Yep. All kinds of medical test data. What else?
Flipping a coin, that's what it is.
Yeah, flipping a coin. So maybe predicting whether it's going to be heads or tails. Every time you scan into the building here, or one of these buildings, it's saying, do you have access or not? And those systems do break sometimes. And if you give someone access who doesn't deserve it, is that a false positive or a false negative? What do you think?
It's false negative.
I'd say false positive.
Oh.
You could frame it any way you want, if you want. But if positive means giving you access, and you shouldn't have given that person access, then that's a false positive. But if you say someone doesn't have access and you give them access, it's a false negative. No, wait. If you say someone doesn't have access, that means you're not giving them access, but they should have had access. Let's write this out. That'll be easier. So we always put predicted, or the output of the system up there, and actual here. So if the actual is you should have access and should not have access. And the predicted, if you say If you say yes to someone who should have access, that's a true positive. Good job, you did the right thing. If someone should not have access actually, but you predict them to not have access, then you're correct. True, negative. Good job. However, if someone in actuality should not have access and you give them access, prediction yes, that is false positive because you predicted positive, but it's false, it's wrong. And of course, false negative down here. What do you think the Gonzaga security system favors? Do you have more of these errors or more of these errors?
Probably want more false negative.
What's that?
Probably want more false negatives.
So some of you think there's more of these, and some of you think there's more of these. Okay, so I've never had my card work when it shouldn't. So if my card worked, if it predicted a positive, if it gave me a yes when it should not, that's here. I've never had this happen. In fact, after your final exam, like hours later, my card stops working. Like if I forget something in the room, I can't get in without help. Maybe for students, they let you come in the summer, but I don't think that works for me. So this has never happened to me, but this has, when my card didn't work, but it should work. That's just a choice that the system makes. And I think it's probably the right choice. Of course, the system is not really a machine learning model, but that gives you a way to think about it. Now, let's take the similar kind of thinking, but we're going to apply it to search. Let's say we're searching in a database for things that match something that we're looking for. Like maybe you're searching for documents about, I don't know, whales maybe. And you search for documents, and some of them actually are about whales, and others have the word whale in it. Like someone said, I had a whale of a good time. And the document is not actually about whales, but it comes back anyway. Search is usually thought of in terms of precision and recall. So let's say the blue dots represent documents about whales. And the red ones are about other things, but they're interspersed. And we have some search function, and it goes into our data set, and it tries to get back to things about whales. So our search query goes out there, and it grabs something like this. So the two things to look at with any search result like this are how many of the results we've got are actually the ones we want. That's the precision. And then how many out of all the results are included in our search set. And that's the recall. So think about this picture up here. Let's kind of do it here. Inside this block is everything we need to do to calculate precision. Precision. We got a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 points total in our results. So that's going to be the denominator. Then the numerators, how many of them are actually documents about whales? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 out of 13. That's a pretty good precision. That's not bad. Okay. Recall. I want someone to tell me how we calculate recall.
Two constants divided by two constants plus constant negative.
Yeah, pretty good. I think that's exactly right. So the easiest way to think about it is, out of all the blues, how many blues did we actually get? So there's 11 blues in here and 2 out here. That means there's, 13 blues total. And we got 11 of them. So it turns out our recall is good too. And our recall and our precision are exactly the same. Is that always the case? What do you think? No? Why not?
It's like if you had gotten so like if it was kind of the other way around and you have like false negatives, I guess, then like you would change the recall.
Right. Yeah, they don't have to be the same. In this case, they are. Now, sometimes it's really important to have high precision. Other times it's really important to have high recall. And this is very similar to the question we were just talking about. Is it better to not let someone in when they should come in, or let someone in who shouldn't come in? It's the same balance you're trying to make. Now, let's say we're talking about terrorists getting on planes. You want to favor your recall or favor precision? You usually can't have both. Okay, go ahead and favor precision. Okay, let's raise your hand. If for terrorists or stopping terrorists getting on your plane, is precision more important? Raise your hand. You think so? So we got 3. Okay. And recall, is recall more important? All right. So for precision, if you're favoring precision, that means everybody you single out, say, you're a terrorist, you're a terrorist, then you're 100% sure almost that they are terrorists. And if anyone's not a terrorist, you never bother them. And, a few terrorists slip through and, cause planes to crash, no big deal. Or let's favor recall. We make sure we get almost every terrorist, but we also bother a lot of other people that aren't terrorists and make them, get interviewed in a room by some cops or whatever. So it's a hard question sometimes, because maybe stopping people and interrogating them is, cutting down on their rights and their freedom. Every society, I think, draws that line a little bit. How about death penalty? Precision or recall? Raise your hand if precision is more important. Raise your hand if recall is more important. If you have recall as your number one thing, you're going to make sure you definitely kill every murderer. You kill a bunch of other people too, but at least you got all the murderers, right? For precision, if that's more important, then everybody you kill is definitely a murderer, but you let a lot of murderers go free too. That's the system we have. You're innocent until proven guilty. However, we've got other problems with the system, and there are innocent people who do get killed too. And there's a lot of projects trying to help that, but precision and recall, this is not an easy thing. Who here has heard of the F1 score? Okay, the F1 score is a score that balances precision and recall. It's important to always think about both. Let's pretend we go back to our search example. And let's say I'm trying to search for documents on the interwebs that have to do with whales, okay? And there's millions and millions of documents. And I want to make sure I get recall perfect, but I don't really care as much about precision. What's the easiest way to do that? What's the stupidest model that can get perfect recall? The stupidest search model.
Says yes to everything.
Yes, just say yes to everything. Every time you make a search, imagine if Google just gave you every document or every web page that exists every time you did a search in no particular order. That would not be useful, would it? But it would have perfect recall. Perfect precision can be done, by having just one document. Give you one and it's correct. Okay, great. That also doesn't help. That's why you need to be aware of both. And the F1 score is the score that incorporates precision and recall and tries to balance them. And you can have different F scores. You can have a 2 score or an F5 score. And these will favor one or the other, precision or recall. So for a lot of your semester-long projects, if it's applicable, I expect to see something like that confusion matrix we looked at in the last slide, or precision and recall like this. Now the confusion matrix, that was applied to just true and false, but it also applies to multi-class classifications. Okay. I need 3 genres of music. Someone give me one.
Not
Rock. Okay. What's another one? Rap. All right. What's another one?
Folk.
What?
Folk.
Folk. All right. So we do the same thing down the left. Rock, rap, folk. So can any of you think of a song that can be both of these? Like 2 of them. I'm thinking of older songs. I'm older than you guys. So Walk This Way by Run DMC and Aerosmith, that would be both rock and rap. So wherever you put it, you're going to get something wrong probably. So one way you can think about this is if something actually is rap and you predict it as rap, it's correct. So let's say we had like 5 songs that were correct. And then there's this one song, the one I just mentioned. Actually, let's say the truth is that it's rap, but I classified it as rock. So the truth is that it's rap, but I classified it as rock. So it goes here. Or if something is actually folk, but I predict that it's rap, it goes here. Let's say there's 7 songs that actually are folk and I predict them as folk, great. If there's 2 songs are actually rap, but I predict them as folk. Let's say there's 0 songs that are actually rock and I predict them as folk. Let's say there's 0 here too. And then for the rock, let's say there's 12 songs that are actually rock and I predict them as rock. And then there's maybe 1 song that's actually folk and I predict it as rock. Now, let's say that there is, remember, this is actual, this is predicted. Okay, name a song that can cross one of these genres, cross two of them. How about Old Town Road? Which genre is that? What do you think? Okay. Does everybody agree with him that it's rap? Yeah? It's not country? Country folk? Maybe. Okay, let's pretend that we got it wrong. Let's pretend that you predicted it's rap, but it wasn't actually rap. Let's say it was folk. Where do I have that? Which stuff?
So I guess it was rap and it was folk. Which one rap?
Yeah, which stuff? Well, there's two folk rap ones. This is folk rap and this is folk rap. It's actually folk, but you predicted rap.
Yeah, so
Right here? That's the rock folk square.
I mean,
Right here? Yep, that's right. This is a multi-class confusion matrix. When I first heard the name confusion matrix, I thought it was a stupid name. Right? It's kind of a silly name. It just makes me confused. But it helps you understand where the model is going wrong and in which direction. Now, if our model was perfect, what general structure would we see in this matrix? Where would the high numbers be, or all the numbers be? Everything would be along the diagonals. Exactly. In a confusion matrix, you can very quickly see if you're doing well. If all the numbers are on the diagonal, you want zeros everywhere else. And when you get things higher than zero off the diagonal, that's where you can understand what your model is doing wrong. And that can lead you to fix things or try different kinds of models. All right. We talked about precision and recall, and this is, it's just a bunch of TNs and Fs and Fs and whatnot. It's a little bit hard to remember all that. Just remember, precision is from the results you get back. How good are they? Recall is how many of all the good results you get. And accuracy is just how many right answers out of all the answers for your model. Sometimes you have to look things up sometimes, but just try to get an intuitive grasp of what these words mean and use your intuition when you can. All right. Now, one of the models we looked at last class was this logistic regression. And all you're doing with this is you start off with some data that's positive or negative, trues or falses. Let's say down here, we have not cancer. And up here, we have cancer. So we have some model that's doing a prediction. And we have a bunch of people who have not had cancer, and they've done a test. And let's say this test looks at your blood results, looks at proteins in your blood, looks at other kinds of biomarkers and other maybe things about your overall health, and gives you one score. Because we're just looking at one X dimension. There can be multiple, and usually there are multiple, but just for simplicity's sake, we're just looking at one X value. And let's say a bunch of people who did this test and did not have cancer, they had scores like this, a bunch of them here and here. And there were a few outliers. Then a bunch of people who did have cancer, most of their scores, their X values, were up here. But they had a couple outliers too. Then we posit a model. And really, it's just something you pull out of your head and hope for the best. That's what a lot of these models are. You assume either a linear relation, or a logistic relation, or a second degree, or third degree, or sixth degree. In every case, you're coming up with something out of your head and hoping for the best. There's no perfect right way to do this. Now, if you understand exactly how a human body works perfectly, which no one does, then perhaps we can build something up from first principles, from biophysics or something, and determine the underlying causes, and maybe that could lead us to the right shape. But until then, let's say we start with this, and we're just going to posit that curve we looked at. The curve maybe goes through these dots here and starts to arc up and eventually goes through these. Now we've got ways we can control and change this curve. We can shift it left to right. We can also make this curve a tighter climb, like a steeper angle, like this. So maybe it has the same center point, but it has, a tighter curve there. And that's really all we can control. It's just two things. Now, a lot of times this green curve will fit the data better, lower error. But it's our age-old problem of overfitting, right? So you need to be able to tolerate some outliers, and sometimes this looser curve, it works a little better. Now, if we took one of these curves, let's say we just chose the blue one, and we did it like this, we're going to have some wrong answers. Like this one, we're definitely going to get it wrong, right? And this one, we're definitely going to get it wrong. Because this person does have cancer, but their X value is very low. So our model is going to say, most probably, it's this one because it's closer. And the distance from here to here, or here to here, think about that as a probability. So if we want to increase our recall of cancer cases, which way should we shift this curve? To the left, exactly. Because if you shift it to the left, more of these will have a higher probability. If you shift it all the way over here, then all of these will be determined to be cancer. They will be positive. Now, the problem is you are also going to have a lower precision because a lot of these will no longer be not cancer. You're going to have a lot of the not cancers lumped into the cancer. So you're going to go around telling people you have cancer when they don't. But maybe that's better, because if you tell someone who doesn't have cancer and then they start exercising and having a better diet, well, it's not like they did it for nothing, right? However, if they do some very dangerous chemotherapy and they didn't have cancer, that could be bad. Or if they had major surgery and had, things that weren't tumors pulled out of their body, that could be bad. So it's always a balance. But that's what this graph is about. Shifting it or tightening it. And again, you have to choose between precision and recall. Which one do you value more? And if they're balanced perfectly, what do you call that score? the F1 score. The F1 score balances them perfectly. And a best F1 score ever is 0.1 or just 1. And the worst is 0. So it goes from 0 to 1. This is not your book, but you should know about it. This is the receiver operating characteristic. There's a good Wikipedia page on it. Think about this as what you should look at to determine that threshold. Like this is our threshold, right? If we shift our threshold to the right, then we get higher precision. But a lot of people actually have cancer, they don't find out. We have lower recall. If we shift to the left, we have higher recall, but a lot of people who don't have cancer get scared. So how do we set the threshold perfectly? So you can think about this as having a threshold way down here, and this line kind of represents moving that threshold up. There will be an optimal point where you would have the highest F1 value. Use your false positive rate and true positive rate. If you shift your threshold a little bit up. So if we start threshold way down here, we're going to get basically all positives. So if our threshold is like 0.01 or whatever, way down here, then everything above 0.01 is going to be considered positive. That's what a threshold means. Tons of true positives and tons of false positives. As we shift our threshold up, you get fewer false positives. So fewer of these, right? We don't want these to be positive, these are false. So as we shift the threshold up, we keep the true positives, but we lose the false positives. This right here means your model is really not doing anything interesting. Here, these are more interesting. What you want is you want your model to be pushed that way, to do really well. So the best curve, called the ROC curve, receiver operator characteristic, the best ROC curve is one that shoots up almost straight and almost hits the corner and then goes to the right. If you want to delve into this more, look at the Wikipedia page. But the area under a perfect ROC curve is equal to 1. If your area is at 0.5, then your model's really not doing anything interesting. That's almost randomness right there. So think about that. The ROC curve, also known as the area under the curve, they might call it AUC. That's another term you might see. You want that to be as close to 1 as possible. Okay. When you're training, you always want to split your data. You don't want to train on the test data. Why is that? You just memorize it. Yeah, it'll just memorize it. And then when you get new data out there in the real world, your model won't know what to do with it. You might be overfit. Or maybe you're doing fine, you don't know. You can't know anything unless you hold out the test. So you have your training sets and you have your test set. What's your validation set? It's a separate set, but what is that? What is it for? What's that?
Sorry, you said validation step.
Yeah, so there's a test set, there's a training set, and then there's this third thing called a validation set.
Well, it's completely separate from the data you trained the model on, and so it kind of provides a third party test on, I guess, to make sure you can pull for training.
That's what the test set's for, though.
It's just to verify that you did it right.
That's what the test set's for.
Was your training set, were you aware of your test set?
Yeah, well, you didn't use it, but you're aware of it.
You were, so you can't just like have your training data to be looking towards getting the higher accuracy on the test set. Can you do that?
Well, what you do, if you have just test and train, you train the training data, and then you find out how good your model is with the test set. But then there's this third thing called the validation set. What the heck is that for? Well, it's good to see it used in an example. There's more than one way to use it, but let's say you're doing cross-validation. You're going to rebuild the same model again and again and again. And yeah.
Validation set, would you have it already defined as in the not ready?
Well, all your sets are like that.
Oh, okay.
So you have, this is supervised training only. You know the right answer in every case. You're trying to teach your model. So cross-validation is a good way to judge if a certain kind of model is a good choice for you. Let's say that you want to see if neural networks are a good example of it. One thing you can do is you can split your data up. Let's say we split it into 5 folds, they call it. K-fold, it just means K can be anything. Let's say it's 5. So we have the same data split up into 5 different sections. And we're going to train and test our model 5 times. And then at the very end, test it again. So that's kind of like having 2 different test sets in a sense, right? You got to start off by pulling out your test data. So if you're doing 5-fold, your test comes out before you even start that. So see how the test data is separate up there? It's like a 6th section. When you train your model the first time, you hold out this. This is not your test data, but it's another holdout set. That's a kind or situation when you can call it your validation data. So that's what validation data is. It's like test data, but it's done separately during your training process. So let's see what this is. That first time we train the model, we have our 5 sections of the data, 5 folds. The first 4 we use to train, and then we test on the validation folds in the orange. Then we start over from scratch with a fresh, untrained neural network again, the same model, okay? And we train on the first and the 5th one, then test on the 4th. Then we throw that away in a sense, or we maybe save it, but we start over from scratch again with the same neural network. We train on the first 2 and the last 2 and train and test on the validation fold in the middle. We do this 5 times. And every time we test it on the validation set, we get a different accuracy. So mean squared error. And let's say these are them. Then we can take the mean of these, and maybe we get this. And if that's good or bad, that could tell us how good this neural network is. Then we can do the same process from beginning to end with a random forest or some other model, right? Then when you're totally done, and you've chosen your model, then you test it on the test data. Now, there's some reasons why you would do this instead of just testing on the test data each time. And that's because when you're going through your process of selecting your models with the validation set in mind, that's kind of cheating. And you might select a model, even if you didn't train it, you might select a model that happens to be overfit to your data. That's why you separately treat your test data and your validation data. Validation data is best thought of as tiny test sets used during the training process. Questions?
So each of the folds are all the same data, right? So like the fold one and model one is supposed to fold one and model two.
Yes. You split the data once into 5 sections and then run things again and again. So how should you split your data? I prefer this first one. Some people do this. The most important thing to keep in mind is that you need enough data in your training and your test and your validation. Test and validation need to be statistically representative samples. Remember when I talked about what if I only took attendance from the first row and how that wouldn't be a statistically representative sample? Or if I bias my sampling by maybe where you live or gender or what music you like, all those are biases. Now, if you were doing some analysis and your data wasn't randomized beforehand, let's say you trained on a whole bunch of data, but then your test data was all from one geographic location, or all people who have answered a certain thing on a survey. None of them were in the training. We should randomize things beforehand, and then make sure that your validation and your test set are statistically representative. And you can do 10-fold validation or 40-fold. There's a lot of different ways to do this. I personally make sure that my data is randomized, and I don't usually do cross-fold validation. I just do training and validation and then deploy. Okay. Here's a case where you want to make sure that each segment of the data, when you split it up, has a statistically representative sample. So it's not all from one state, for instance. Okay, now here's something called bootstrapping. I don't like to do this, but sometimes you have to do this when you don't have enough data. In this world these days, it's usually possible to get enough data. There's too much data, but let's pretend you don't have enough. So there's some population out there in reality, and you have some sample, but it's a small sample, and it's not enough to train what you want to train. So what we do then is we mimic or we fake samples. We take our sample, let's say, pretend, I guess there's like 15 or 12 things in there. 10. Okay, there's only 10 things in there. We're going to pull out a sample of 5 things from there. And we sample again with replacement. Sample with replacement. So each time we're pulling out 5, but each of those points gets pulled out again and again and again. So we get a lot of repeats. But the idea is to generate samples from our data. That's, yeah, there's a lot of repeats. But if you have a lot of these samples, hopefully you can train a model on it and just kind of hope for the best. This is not my favorite way to do it, but this is what some people do. All right, this is just another example of cross-fold validation or using bootstraps. Say you train 30 models this way. This is something you can do when you don't have enough data. Another time you often don't have enough data is when one of the classes is very rare. Let's say you have a fraud model, and you have some X's that describe every transaction that occur, like on Visa or MasterCard. They have lots of variables, and sometimes there's fraud. Now, if you want to get 99% accuracy, all you have to do is have a stupid model that says not fraud, right? Just a function of return. It's not fraud every time. It will be 99.9% accurate because most situations are not fraud. But what if you want to do better than this? You look at the data and there's hardly any fraud cases. How do you get more fraud data? Well, one thing people do sometimes is they take the fraud examples and they artificially make more of them. And then for the not fraud examples, they artificially throw some out, thus making the data set more balanced. I don't love this either, but sometimes you gotta do it, and it helps. SMOTE is one technique. Synthetic minority, meaning the fraud class is the minority class. Synthetic minority oversampling technique. So if we have some data set where it's mostly blue, there's not enough oranges to really build a good classifier. You want to get more oranges and fewer blues. So you just do this synthetically. You come up with other fake oranges that are nearby other oranges, and you throw away some of the blues. Then that gives you a more balanced data set. But remember, it's fake data. But even though it's fake data, sometimes it comes up with a generalizable model that works better than what you would have trained with the real data. So what I hope you're starting to see is that there is no one silver bullet. There's no one right way to do this. There's a bunch of little tricks, and think of it as your bag of tricks. You try different things, and you do your best to have a sound mathematical grounding for everything you do, but sometimes you're just guessing and see what works. Now, another way to model is an ensemble model. Ensemble just means together. So you have multiple models predicting on the same thing. And you train them all. And it could be the same model trained on different subsets, maybe using the bootstrapping technique where you're sampling with replacements. And you just train the same model 100 times or 1,000 times. This is often what random forests are, in a sense. Same data, same model structure, but trained again and again from different randomly chosen variable order. Or it could be 3 totally different algorithms or models, or 100 of them. And then you take their output and you average it. Or maybe if it's classes, the ones that get the most votes, the voting data. Or sometimes these models, you can trust one more than the other. Maybe trust them more in different situations. In fact, there's a guy named Ray Dalio who heads up Bridgewater, so they're a hedge fund, I think it's an investment fund, and they do this with people in their company. So he has a system that I think that he'll use, but he talked about in one of his books, where whenever you're in a meeting and you're listening to other people talk on a given topic, people in the company will be voting each other up or down on credibility, on how much we should trust that person. And the system overall takes those votes and helps the company make decisions. Like if you're talking about something that involves mechanical engineering, the mechanical engineer in the room should get high credibility, and his vote should come to more. But then if you're talking about psychology, his vote should count less than the opinions of a psychologist. You can treat models the same way, where some models work really well in certain parts of the space, sample space, and other models work better in other parts. Here is another example of how an ensemble model can be used. Let's say you're trying to divide up a region into maybe 3 sections based on some parameters. And you have 3 different models that give different predictions of where these lines should be. Maybe it's not properties in geographic space, maybe it's X1 and X2, and you're trying to figure out some Y. Whatever it is, you have all 3 models partition the space into those three sections. And then you get some disagreement here. There are some points that could be on one side or the other. So you average them out, you get this. And sometimes this averaged ensemble model is better than any one of the models that went into it. I've done this a lot and had success with this. Any questions before we start chapter 9? All right. Most of what you're doing for your semester long projects are supervised models. We're going to talk about supervised and unsupervised means you know the right answers. You got inputs, you do a bunch of X, X1, X2, X3, X4, and there's a Y. Some output variable you're trying to predict that you know the right answer. In this case, I guess they're trying to predict condition. And the X's, X1, X2, X3 are these. So we have a bunch of input variables, input X's, and we're trying to predict that one Y, the condition of the house. Try to predict the condition based on when it was built, or it was renovated, or bathrooms, square foot, all those things. Supervised model. We can use things like regression, we can use neural networks, we can use a lot of the things that we've been talking about. If you try to predict the price, that's another supervised model. What company is very famous for predicting the price your house might sell at? Zillow. Zillow. Does anybody know what happened to Zillow about a year ago? They had this whole division of the company where they were flipping houses. They were buying them, fixing them up a little bit, and selling them. It was back when houses were going up still, during the best housing market of my lifetime, definitely of your lifetime. But what happened to Zillow? They lost $1 billion doing that. They had to end up laying off 25% of their workforce. That was during the best housing market of my lifetime, when houses were going up the fastest. There's something wrong with their model. Does anyone have a guess of what it might be? The way the model would work is they would, for any house in America, they predict the value that it sells for right now, right? Then they could go to that person and offer them just a little bit less, buy from them, and then fix it up a little bit and sell it for more. That's the theory. And it really should work. It does work for some humans. There are people who made a career on flipping houses. I have a friend doing it right now in Spokane. If you're a human, you go to a house, you can see things that aren't in the data. Like, what kind of things could you see that you'll never see in a call data set?
Maybe like the ceiling is leaking or something.
Yeah, there could be leaks in the ceiling. What else? Neighbors. Neighbors. Maybe your neighbors are jerks.
Asbestos.
Asbestos. Yes, there could be asbestos in the wall. What else?
Noise incident.
Noise neighbor, you could be right next to the train. There could be gunshots in your neighborhood. Those are things that, some of them at least, are not in Zillow's data set. Remember that airplane I showed you with the red dots on it? And there was a survivorship bias. So the airplane came back, all the airplanes that would come back, they would chart on that diagram of the airplane where the bullets were, right? And there were places where they didn't have any bullets, like there were no bullets in here where the pilot sits. And it's because, you know, those planes didn't come back. They don't have those data points. If you build your model when you're missing some very crucial data points, that can be bad. You have to be aware of these weaknesses. Now Zillow, everything in their model is based on house sales, sales that actually occur. There are houses that have not sold even once in the last 20 years. Zillow still makes a prediction on those. Maybe they didn't sell because they're just really ugly. Maybe there's some festering growth in the front yard that just makes it look disgusting and no one wants to buy it. But Zillow's algorithm can't see that, so they offer this high price. And the human who lives in that house says, oh yeah, I'm selling right now, sure. Because they know that no one else would offer them more. And then Zillow is now stuck with it because they trusted their model. There's another concept that could cause a problem. And we'll end with this. Some systems cannot be treated linearly or even smooth. All the models that we've looked at, when we have a bunch of dots, we have some model that goes through them. Maybe the model is a straight line, maybe it's a curve, maybe it's a tighter curve, but in all cases, it's smooth, right? And there's a lot of mathematics behind smooth curves, and there's Cauchy integrals. There's a lot of neat stuff if you ever want to look that up. But there are realities sometimes that make breaks, non-linear things where maybe there should be a model that, you know, goes like this and then stops and starts up here and then does it again. This is one of those situations. Imagine we have a set of rules for what to do from one time step to the next. So we have black, white, and gray squares here. This part of the rules, this is all the rules. This tells you, for this one in the middle, what color should you make it given the three that precede it. So think about this as the first day, this is the next day, or next time step, next time step. So if you have black, black, gray, then the middle one should be white. Black, black, white, the middle one should be gray. Simple, right? So determine this, there's no confusion at all. Then we're going to do a run, that one up here at the top. We'll have an initial state. See that initial state there? It's just some black and grays and whites. And we see how it changes day to day to day to day to day. Do it again, but with a slight change to the initial state. Just one change. Instead of black, 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 it's white, black, black, black. Almost everything is the same. Same thing here. So we're doing it 3 times with tiny changes on that initial state. The differences are so small, think about them as the flap of a butterfly. This is where chaos comes from. The math of chaos is. That tiny change over time with the same simple rules, it makes radically different futures. This is radically different here than here than here. They're not even correlated anymore. Now, if this kind of thing could be applied to housing prices, let's say you have a neighborhood with some houses, and make one little change, like a meth lab moves in next door. That's going to change the value of those homes. Or what if they, make an awesome new little outdoor shopping mall with a Starbucks nearby? That could also change the value of the homes. These little changes over time are non-linear. This concept is called computational irreducibility. Most of the models you're going to learn how to do this semester can't handle this. And that is another reason why Zillow failed, in my opinion. That's good enough for today. Thank you, guys. I'll see you on Thursday.
Training.